This is my video report for Lab 2, motion of a falling object. For this lab, we had to set up an experiment in order to analyze position versus time relationship in 3 distinct cases. First one, observed position versus time model was obtained from Tracker. In cases 2 and 3, a computational model of the same position versus time graph was built in GlowScript using Python code. One includes only the gravity and the other one includes both the gravity and the drag effect. For my experiment, I have analyzed a paper ball falling from a certain height from rest, meaning that the object's initial velocity was 0. Its acceleration equals g, or 9.8 meters per second. For calibration, I have used the height of the guy throwing the ball, 1 meter 90 centimeters. So this is my video. Here I have summarized a few most important concepts: Newton's second law, the knowledge of what the drag force is, and the fact that forces acting on a moving object or any object at all strive for equilibrium. On this slide, you can see a screenshot from my Tracker video. I have set the coordinate axis right in the middle of the paper ball when it was still in the starting position. For the time intervals, I have set t equal to 0.033 seconds. Also from the table in the bottom right, you can see how the x coordinate changes just a tiny bit. That proves that the majority of motion is happening in the y direction. Since the object is falling down, we're going to use u-coordinate to track the change of position of the object. The position versus time relationship looks like a half of the parabola facing downwards. It's not a straight line because the object is falling with the acceleration, and it has a negative slope because acceleration and the motion in general are happening in the negative y direction. In the code for the computational model with gravity force only, on line 44 we have set the gravitational constant b equal to 0. In the recursive loop, I have first set t value to 0.5. This is exactly how long I was observing my object in the experiment. Then we have set the net force to be equal to the only force acting on the ball, which is minus mass times g and times g hat, which is the only vector in the positive y direction. On the line 69, there is a velocity update equation in the form v final equals v initial plus acceleration times delta t, where acceleration according to Newton's second law is net force divided by mass. On the line 79, there is a position update equation in the form final position equals initial position plus velocity times delta t. And there were several ways to obtain the position versus time graph for the gravity and the drag case. I have chosen the following. I have left the drag constant equal to 0, but in the recursive loop I have created another variable for terminal velocity, because in this case both net force and acceleration are 0 and therefore the velocity is constant. Then I have calculated both drag and gravity forces, and finally I update velocity and position. Both are only changing in the y component, so therefore the velocity vector is 0, minus g times t, 0, and the position vector is 0, v times t, 0. On this slide you can see all three models on the same plot, and as expected, Tracker video is at least precise of them all, because there are a lot of factors such as, for example, human error that blur the result. We can also see that the curve that corresponds to the model with drag force is a little bit more flat, because as we know, drag force acts in the direction opposite to the direction of the motion. On this slide, I have answered the question whether any of the models predict the terminal velocity, and the answer is yes. In the case where both drag force and gravity forces are included, we use terminal velocity, because since acceleration and net force are 0, velocity is constant, so this constant velocity equals to terminal velocity. And here on the last slide, I have explained the situation if the object was falling not from rest but with a certain velocity already. So if we use the formula where final velocity equals initial velocity plus acceleration times delta t, we can obviously see that the terminal velocity will be larger because the initial velocity is not 0 but something else.